Hello. In this video, we're going to demonstrate Lab 10, semiconductors. So for this video, the semiconductor that we're going to use is a diode or diodes. We're going to connect the diodes, we're going to measure them with an ohm meter, and then we're going to connect them in a variety of DC and then AC circuits. Okay, so the first thing that we're going to do is an ohm meter check on our diodes. So if we look at the schematic, the first thing we're going to do is a resistance check. Now, depending on our meter, the resistance check may or may not be very useful. What we would expect is to have a low resistance in one direction and a high resistance in another direction. But diodes don't always cooperate, and the meters don't always measure them accurately doing resistance checks. So most meters come with a diode check option, which is a lot more reliable. So, all right, so let's take a look here. This is the equipment that we're going to use. We got the oscilloscope. Here's my transformer. It's a 10 to 15 volt AC transformer. And then we have the DC supply. All right, so here the first thing I'm going to do is take one of my diodes. This is a silicon diode. Notice the white or light gray line. That's the negative side of the diode. And so I'm connecting the diode between my yellow and blue connections on my breadboard. I'm going to put the ohm meter or the digital multimeter in ohms, and I'm going to measure it first when it's forward biased, which means red to the positive side of the diode and black to the negative side of the diode. Now I would expect this to be a low resistance, but with these green meters, it's still reading 8.9 mega ohms. Depending on your meter, you may get a wide variety of different values, but we're just going to record what we got. And so we got 8.92 mega ohms. Okay, so next what I'm going to do is swap the leads and do get the connection when it's reverse biased. So in this connection, the red lead is to the positive side of the diode. I'm sorry, the red lead is to the negative side of the diode. So I have the line right here. So that's, and we would expect this to be a high resistance. And for this one, we get OL. So with this check, even though our resistance wasn't as low as we would like it to be, we did get two very different readings. We had some connection and then over. Now typically the diode test is much better, so we're going to do that next. So I'm going to put my meter in diode check. Now you got to be careful because on this setting there's diodes and then continuity check. So I may have to select until I see the diode up here. Okay, so now I'm going to connect forward biased, so that would be red to positive, black to negative, and for this I should see about 0.7 volts for a silicon diode. And this is a voltage measurement, not a resistance measurement. This is measuring the forward voltage drop, and it looks like 0.556 volts. Now again, some meters won't show that, so you have to be careful. If it's a voltage measurement, if it's in diode check, it should be a voltage. So here we'd have 0.56 ohms, or I'm sorry, just did it again, volts, or we would say 556 millivolts if we were doing proper engineering notation. Now I'm going to swap the leads, so now I have red to the negative side of the diode and black to the positive side. This would be reverse bias, and so this one is OL. This would be OL volts for that one. Notice that this still has the volts there. Okay, so now I'm going to go to the next part, and the next part what we're going to do is we're going to construct a DC circuit. So notice we have DC here, and we have a diode and a 1 kilo ohm resistor. So on here, that's what I've connected. Oops. So if I look here, I have my yellow here, and then the connection between the diode and the resistor is blue. That's this connection. And then the other side of the resistor, we have pink here. It's not a perfect pink, but that's okay. And then the other side of the ammeter is going to be connected to the negative. And so we're not going to highlight that, but I just wanted to show how the breadboard is connected to the picture here. Okay, so we connect it. I verified that it's a 1K. So I'm going to take my meter, put it back in milliamps. I've got to move the lead over. The on here, the red lead is the positive, and then the black lead is the negative. So I need the red lead connected to the pink socket here, and then the black lead is just going to go back to my negative on my DC supply. So we have the DC supply here. I'm going to use this little socket, and then the positive lead, the red, that's going to go to the diode in the yellow socket. Let's zoom in a little bit here so you can see this a little bit better. And the black lead goes to the meter. So I have the red lead coming in here to the yellow, going to the positive of the diode. The negative of the diode is connected to the resistor. The other side of the resistor goes through the ammeter, through the red, through the ammeter, back out the black lead, and into the terminal. All right. Okay. So now we're going to turn the power supply on. We need 12 volts, and you'll notice that as soon as I get voltage, I get some current to flow. And it looks like I have 11.3 milliamps of current on there. So my current is going to be here, 11.3 milliamps. And then next I'm going to grab my other meter, put that in DC voltage. The 20 should do it. It's below, we only have 12 volts max in this circuit. And I'm going to measure the voltage across the diode. And I get, let's see, it looks like 0.73. Or this would be 730 millivolts. Now notice how that the voltage drop here was not the same as the voltage when we did the diode test. Diodes are nonlinear devices, so as I push more current through it, the voltage drop across it gets higher. And so that's something that we would see with diodes. And so typically we assume it's a 0.7 volt drop for silicon diodes. That's because at about 12 volts we get pretty close to 0.7. All right, now I'm going to measure the voltage across the resistor, and if I do that, I get 11.22 volts. And if I add these up, I get pretty close to 12 volts, which is what I would expect. Okay. Now I'm going to swap the diode around. Notice how this diode is in different orientation than that one. So I swapped the diode around. Now the negative on the diode here is connected to the red, so it's reverse biased. So now notice how when I turn the voltage supply on, I don't get any current. So this would be 0 amps current. The diode in this circuit is an open, so we would expect to get the full voltage across the diode. And so now I'm going to measure the voltage drop across the diode, and I do get 12.08 or 12.1 volts. And then I should get 0 across the resistor, which I do. Try to measure it a couple different ways here just to make sure that I'm making a good connection. And I get 0 volts there. So I get the full voltage drop, the full supply voltage over the open diode, and I get 0 volts across the resistor. So I have 0 volts, I would get 0 amps through the resistor. Okay? All right, so the next one that we're going to do is the rectifier circuits. Now, our circuit is a little bit different than this because we have a different power supply, or a different transformer, excuse me. So I'm going to draw this one a little bit differently. So we have our power supply, 120 volts, and that's going to be connected. We have a not a center tapped transformer. And last time in our last lab, we found out that that was an 8-to-1 transformer. And then we're going to connect that to our diode and then our 1K resistor. So this is our 1K. Okay, so what we would expect if we have 120 volts and an 8-to-1, we would expect to get 120 divided by 8 on the secondary. Now that's going to be the RMS voltage. So that's 120 to 15 volts, even though that's not exactly the label that's on that transformer. So this would be 15 volts AC. Now, if I was converting that to peak, the voltage peak to peak would be, or let's do the voltage peak, that would be 1.41 times 15. So if I take 15 times 1.41, I would get 21.5 volts peak. Now that would be the voltage here would be 21.1 volts peak. Now I would expect to get 0.7 volts drop across there, so my voltage that I should get across my resistor would be 21.1 minus 0.7. So we would expect to get 20.45 volts peak across that resistor. Okay? And so what we're going to do is we're going to connect the oscilloscope across the resistor, sketch the waveform, and then we're going to make the following measurements. But we think that the voltage across the resistor should be 21.45 volts peak. That's what we think we should get. All right. So this one was a little tricky because my transformer, I had a plug that I could plug into it, but it didn't make a very good connection, so I ended up cutting the wires on this. So the first thing I do is, if I go back here, this diode for the last one is reversed bias. So the first thing I got to do is flip the diode around to make sure that it's forward biased. So I want the line on it to be pointing to the right. And then I cut the wires here, and I probably should have used a wire nut or something like that, but I just twisted them to these solid wires here. So I have positive and negative. And here my diode is forward biased, and then I have my resistor. Okay, and then what I'm going to do next is I'm going to get the oscilloscope out, hopefully. All right, and I'm going to connect the oscilloscope probe leads across the resistor here. So here's my oscilloscope probe leads, positive and negative. And then I'm going to connect my voltmeter across as well. And so I'm going to put this is on volts AC right now. I'm going to leave it there. I want to know the volts AC and the volts DC. So both probes, the digital multimeter and the oscilloscope, are across the resistor. All right, and then I'll plug it in. This will turn on the transformer. So notice I have some AC voltage here. And then I'll turn this on. This should be at 9 volts to power up my oscilloscope. And it takes a moment here for it to boot up. Okay, and then what I did here was I moved the signal down, and you can see that the signal is still moving. When we go to 60 hertz, it's kind of hard for the oscilloscope. We have to stop it in order for it to stop the waveform from moving. So, all right, whoops, just a minute here. So let's look at the oscilloscope, and it's really hard to read here, but that's 20.7 volts peak to peak. which peak to peak here is what we would actually call voltage peak. You can barely see it, but it's 11.1 volts RMS, and that's a different formula than what our meter will read. Our meter is calibrated to calculate RMS with a sine wave, so it doesn't get the exact correct RMS here. Okay, and so, whoops. So let's write down our measurements here. So the waveform that we would get looks like this. It's a half wave signal. We're clipping off the bottom. The volts AC is 8.19. That should just say voltage there. Okay, and then it looks like we had 20.1 volts peak on our oscilloscope. It's a little tough to see, but it looks like 20.7 there. I think that's what it was. And then when we went to volts DC, we got 6.42 volts DC. So that's what we would expect here. The way that the volts AC and DC is calculated, there's formulas for that. That's kind of above this class. The volts DC, typically we would call this the voltage average, and this is the effective voltage. And typically the volts AC is higher than the volts DC for this type of signal, and we'll learn more about those in other classes. For this lab, we're just trying to make the measurements. Okay. All right. Now the next one that we're looking at is a half wave, is a full wave rectifier, and this one only works if you have a center tapped transformer, which we do not. So what we're going to do instead of a full wave rectifier is we're going to do or what I did in the lab was a bridge rectifier. Okay, a bridge rectifier is used when you don't have a center tap transformer, and it requires 4 diodes. Now my kit that I was using for this has 4 diodes, but I don't have a center tap transformer, so I switched it to the bridge rectifier. The circuit for that looks like this. You start with an AC supply, and then you have a transformer. Now we had an 8-to-1 transformer, and then now this part gets a little bit maybe strange, but we put the resistor here, and then we put the first set of diodes here. Let me zoom this in a little bit. So the first diode we put here, and then we put another diode here, and these 2 diodes are going to pass current together. So when the supply is positive and negative here during the positive cycle, these 2 diodes are going to be used. And then what we're going to do is we're going to add 2 more diodes like this. And these 2 diodes are going to be used during the negative half cycle. And what's going to happen is we're going to take a signal that looks like this, and we're going to turn it into a signal that looks like this. And that's the bridge rectifier circuit. Okay, so the way that I did this one is I made the connections here is the yellow connection that I made, and then the blue connection is here. And then I connected the one set of diodes to the positive. Oops. I want it to be back on the highlighter. We'll do light red, I guess. So these and these connections are going to be the positives on my board. I probably could have did positive and negative, but that was fine. So, all right, so let's look at how we made these connections. All right, so here is my board. So I have my diode here. Notice the polarity of the diode. So I have the two red connections here and the two red connections here. And then I make 1, 2, 3 in the yellow and 1, 2, 3 in the blue. So if we look at our diagram here, the direction of the diodes is important. So I have the line here and here on this one. It's like those two are negative to negative. And these two are positive to positive. And the resistor is in between. And you notice the resistor is connected between the yellow and the blue. Okay. So now what I'm going to do is I'm going to connect my positive and negative leads to the top and the bottom. So that's here and here. So this one is actually my negative lead off of my transformer. And then I'm going to connect the oscilloscope across the resistor and the digital multimeter across the resistor. And this one was a little tricky, so it took me a couple chances there. Okay, so we have it connected. Now I'm going to turn on my power supply. If you notice right away, my DC voltage is shown. And I get 12.05 volts for the DC voltage. And then you can see on the oscilloscope the waveform that I get looks like this. Kind of like that. I have a hard time drawing it. Okay, so you can see that here. And then if we look at the oscilloscope here, this one we went in a little bit farther, so we can see that the voltage peak to peak is 19.9 volts. Now, the oscilloscope reads that as volts peak to peak, but that means the bottom to the top. So this would be our voltage peak is 19.9 volts. And it looks like the RMS voltage on the oscilloscope is 15.1 volts RMS. Now we're going to actually get that off of our meter. You notice that says the frequency is 120 hertz. It's because we're getting 2 cycles per 1 cycle, so it's double the frequency of 60 hertz. And okay, now if we flip the meter over to looks like it's still on AC, and we flip it to, or it's still on DC, we flip it to AC, we get, in this case, 6.22 volts AC. This would be volts DC, and this would be volts peak. Now, one of the things, and we didn't do it yet, but we didn't figure out what the theoretically should be. The transformer is the same, so we'd start with 21.1 volts peak coming out of our transformer. So we still would have 21.1 volts peak. And what we would expect is that the voltage across the resistor to be 21.1 minus 2 diode drops, 1.4. So we would end up with, what would that be? 21.1 minus 1.4. We end up with 19.7 volts peak. This would be our theoretical voltage peak. We have 2 diode drops, so it would be 0.7 times 2, which is 1.4. And we ended up with 19.9 volts peak in the experiment here. And okay, so that's the end of that video. So we're pretty close. We expected 19.9 volts peak, and we had 19.7 volts peak. Okay, so that's the end of this video. Thank you.